Today we'll be considering some more properties of matrices from Gunning's An Introduction to Analysis. In particular, we're going to be considering the idea of equivalent matrices so we can prove something about them. With that, let's begin analyzing this. We say that two n by m matrices A and B over field F are equivalent matrices if there exist non-singular, i.e. invertible matrices S and T of the appropriate sizes, such that B is equal to SAT. This is a basic equivalence relation among matrices. However, there are other equivalence relationships that are of equal importance and even greater interest that we will discuss later. To check this equivalence relation, we must show that it is reflexive, symmetric, and transitive. Clearly, we have reflexivity and symmetry by the fact that if to show that matrix A is equivalent to itself, we let S and T simply be the identity matrix of the appropriate sizes. And for symmetry, we take the inverses since we're saying S and T are non-singular. And so we take inverses and then we have the correct form. To check for equivalence, let's assume that B is equivalent to A and C is equivalent to B. So we have our two suppositions for transitive, so we want to show that A is equivalent to C, or by symmetry that C is equivalent to A. If B being equivalent to A, that means that B is equal to SAT, and C equivalent to B means C is equal to UBV, where everything is a appropriately sized matrix that is invertible or non-singular. To show that C is equivalent to A, we need to construct appropriately sized matrices, and we simply do that by saying C is equal to this. And the way we can check this is by noting that since matrix multiplication is associative, we write it like this, but we see that if we regroup this SAT term becomes B, and then this entire expression is equal to C. And then when we undo it, the reason we grouped it like this is to express the fact that to show that it's actually equivalent, we need to show that they're appropriately sized non-singular matrices. And we note that the product of two non-singular matrices of the same size will give you another matrix of the same size that is non-singular. We'll recall that this is because the set of non-singular matrices of a particular size over the same field F form the general linear group of that thing, which is of course a group. Therefore, it's closed under the multiplication operation. So these are elements of GL of n, general linear group of size n. So US will be an element of GL of n. And we see that that means that this in total is an n by n non-singular matrix. So it obeys the definition. Here's one non-singular matrix, and here's another one of the appropriate size, so that C is equivalent to A. If we view this matrix as a mapping from Fm to Fn, and you say that it takes x to y, in the sense that y is equal to a x vector, it is natural to ask what matrix represents this linear transformation after a coordinate change in Fm and Fn. That is, you have this mapping between these two elements, but what if you relabel the coordinates of your domain and codomain? How would you represent this mapping still, even though the coordinates have changed? But it still maps the same elements to the same elements. Well, we'll recall the coordinate change is an isomorphism, but from a set to itself. So we say that we choose it to be isomorphism T, and it sends the vector x prime to the vector x, such that this is true. And you do the same thing in S, since we're going to have a coordinate change in Fn. This will give you y prime is equal to sy. Thus, making the substitution to the equation y is equal to ax, we get that y prime is equal to sy. We said y is equal to ax, so this is sax. And then we remember that x was tx prime, so this is satx prime. But remember we said that if we have this, then we have the equivalent matrix B, so that we get y prime is equal to bx prime, where b is equal to sat is equivalent to a. In this sense, equivalent matrices describe the same linear transformation, but expressed in different coordinate systems. Alternatively, the equivalence of matrices A and B can be expressed in terms of linear transformation defined by these matrices as the assertion that the following diagram is commutative. To explain this, let's get into this a little more deeply. We let the arrows in each of these indicate mappings. In this case, these are linear transformations, and we denote that we'll apply A, B, S, and T to be as we had before, but in this case, we had A, B, S, and T are matrices representing mappings. In this case, they'll just be mappings. We'll just view them exclusively in their mapping form. And we'll note the notation iso means that the linear transformations are isomorphic. Recall that commutativity means that you can do things in any order you prefer. So to say that a diagram such as this is commutative means that any two sequences of mappings in the diagram that begin at and end at the same point are equal. For instance, let's consider mapping going from FM to FM. Say this is commutative, let's choose one path. So AS is one mapping to go from this FM to this FM is the same as T inverse B. To see this equivalent to B is equal to SAT, we know that this is the same as multiplying by T inverse on the right. That is, you apply T inverse first and then B, which is the same as applying A first and then S. And then that matches with our definition here by multiplying by T inverse on the right, where the first term on the right is the first thing you apply. So first you apply A, first you apply T inverse, then you apply B, then you apply S. And you see that if you multiply by T inverse on the right on this equation, then you'll get that same thing. So in this case, this can only mean that the mapping in the path B is equal to the result of first applying the mapping T, then A, then finally mapping S. So they did slightly different, which is saying FM to this FM is same as T A S is the same as B. So that means that B is equal to SAT, where because you say that T is first, you need to go from right to left. Which is just the assertion, as they mentioned, is B is equal to SAT. Commutativity of diagrams is a very commonly used notation that can simplify a lot of statements of equality with various combinations of different mappings. However, the notion of this idea of equivalence of matrices can be like considering equivalence of matrices, you can have another problem, which is classifying things. Namely, does an equivalence class of matrices have a simple standard representative, and are there simple invariants that determine when two matrices are equivalent? This is what leads us to our first theorem about equivalent matrices. It's theorem 1.15 in this book, which says if A is an Fn by n, that means it goes from Fm to Fn, is a matrix describing this linear transformation, then there are non-singular n by n matrices S and non-singular n by n matrices T, such that the matrix SAT is equal to B is equal to Bij, has the entries Bij is equal to delta Ij, for 1 from Ij up to K, and 0 otherwise, where m minus K is the dimension of the kernel of A. Thus, that means you can write that B, you can write B in this particular form. So before we get into the proof, we can think about this kind of naturally, is if we say S and T are coordinate transformations of the respective spaces Fm and Fn, then we see that for any transformation A, if you change the coordinates, you can rewrite this transformation A as a transformation B, where you can say, okay, all this transformation does is send this basis vector to this other basis vector in a one-to-one correspondence, namely as a delta, like in the form of a delta vector. That is, the first vector gets sent to one copy, the first vector in the basis of the first space gets sent to one copy in the first basis of the second space, where and no other copies of elements of the second space, and so on and so forth, for up to k elements, for up to k vectors, because the m minus k is the dimension of the kernel of A. So that means the rest of those m minus k terms get sent to the 0 vector in B, and therefore the mapping sends it to 0. And so we note that this is up to, that when you're sending these bases of Fm and Fn to each other, that's after you transform them into the appropriate form using S and T. So let's get on with the proof, which is a little more involved, but has that same essence. Let's consider the kernel of the linear transformation and have it have dimension m minus k. We choose vectors vk plus 1 up to vm in Fm, which will form a basis for the kernel. So remember that we're kind of implicitly applying the rank nullity theorem in the sense that we're letting k be the dimension of the image and m minus k be the dimension of the kernel, such that m is the dimension of the domain. So we're starting from F to M, this domain. So its kernel has dimension m minus k, and its dimension, and the image of it, or the dimension of its image is going to be k. And we're going to use this to form a basis of f to the m. And next, we'll expand this to a full set of vectors, which will be a basis of f to the m. So we'll add an v1 up to vk. We'll then note the image vectors of each of these vi's as wi is equal to avi in fn, which are going to be linearly independent. This is because if we could write the zero vector as some non-zero sum of these, we apply the linearity. If this were true, then the set of vi's is a non-trivial vector in kernel of A. However, we'd say that this would be impossible since this vector is not in the span of this basis. That is, a basis includes everything in the span. So if this were true, then you'd find something that's not in the span, and that's a contradiction. Therefore, it cannot be true that these are linearly dependent on each other. Note that these vi's are up to vk. So all these vk's have images that are linearly independent. We now extend these first k elements, namely the images of avi, into a basis, w1 to wn, for the vector space f to the n. Next, we'll introduce the following isomorphisms. Let t take f to the m to f to the m, so it's a coordinate change, for which t of delta I is equal to vi. That is, you have m basis elements, so you just take the first k of the basis and send them to the non-trivial basis elements, namely the first k of them, and then the rest you send to the trivial ones, i.e. the ones that form a basis for the kernel. And then you do another coordinate transformation S, which takes the wi's, i.e. all the ones that are either in, remember wi's were defined to be the image of the first k vectors, so you send each of these to the first delta I, and then you extend, and then you take the rest of them from k plus 1 up to n, and you send those to each of the basis vectors in the future. Note that that this will just form a full standard basis for f to the n. And now we let b is equal to SAT, which is a map from fm to f to the n, because the first one's a coordinate transformation, here's the actual transformation, and then another coordinate transformation. Let's see what this does on each of the basis elements. Well, each of the standard basis elements. Well, b of delta I, since b is equal to SAT, then we see b of delta I is equal to SAT of delta I. T of delta I we define to be sending delta I to vi, and since we're looking at the first k of these, this will send it to SAVI, and then AVI, since in the first k, is going to go to WI, where I is from 1 to k. So it's equal to S on WI, which by definition is delta I. So we have that it sends the delta ith element of the original basis to a delta I element of the codomain basis. But on the other hand, if you have any of the k plus 1 elements, any of the elements from the trivial basis, namely from k plus 1 up to m, then b of delta I is equal to SAT of delta I is equal to AVI, and remember AVI for I sufficiently large from k plus 1 to m is going to be the zero vector, and a linear transformation on a zero vector will be the zero vector. This means that if we look at the matrix B, that BJI is equal to delta IJ for I from 1 to k. That means that you get sent from 1 to exactly one other delta element. One element of the basis to another element of the basis in a one-to-one way for the first k of these, and that for the remaining set, they get sent to the zero vector. Therefore, we have zeros in those remaining positions. Therefore, the matrix has the desired form of B is equal to a k large I by I, a identity matrix of the size k by k, and the rest are zero vectors. With that, we've proven a lot about equivalence, so we're going to see if next time we're going to prove some more information about this normal form. Thank you.